Hey everybody, welcome to another abstract algebra video, a follow-up to the last one in which I want to talk about another important result regarding homomorphisms. Let's let E' be the identity element of G', and that subset there indicated by the red oval is called the kernel of phi. This is a subset in G, and it is all the elements of plain old G that get taken to E' by phi. In fact, it turns out that the kernel of phi isn't just a subset, it's a subgroup, and it's not just any subgroup, it's a normal subgroup of G. I'm not going to prove that in this video, I'll save that for a later one. But for now, let's look on over to capital G'. I want to pick out any arbitrary element of G' that gets hit by phi. And again, just call it lowercase g'. Next, I want to mosey on over to plain old G and just pick any one of the elements that gets mapped via phi to G'. Let's call it x. And here's the claim. Here's what I'm going to spend the majority of this video proving. Let x there be an inverse image of G'. So basically what we were saying earlier. It's just an element that gets mapped from G to that lowercase g' and capital G'. The claim here is that all the inverse images of G' are contained in the set x times the kernel of phi. Or equivalently the kernel times x, because again, the kernel is a normal subgroup. And secondly, only inverse images of G' are contained in that green set, x times the kernel of phi. Now y'all, before going on, I want to come clean about the definition of an inverse image that I used in the claim above versus the actual definition seen in the more formal mathematical literature. Formally, an inverse image is actually the entire subset of capital G that maps to a given subset of G'. So really in that claim I should have said let x be a member of the inverse image of the set containing just G', but just to minimize the amount that I have to write on the screen and the amount that I have to orally verbalize, I'm going to go with that definition above, but just be aware that the formal definition is slightly different and I'll link to it in the description. Now that being said, let us start on this proof. First we want to show that the only elements contained in x times the kernel are those that map to lowercase g'. And we can proceed like so in proving that. Pluck any element arbitrarily from the kernel, let's call it lowercase a, and notice the following. G', of course, is phi x, but phi x can be written as phi x times E'. E' is the same thing as phi a by the definition of a kernel, and by the definition of a homomorphism, we have G' is phi of xa. And hence, since xa is an arbitrary element of x times the kernel, just a representative, can represent any element in x times the kernel, every member of x times the kernel has to map to lowercase g'. And finally, the second part of this proof comes by way of this question here. Are there any inverse images of lowercase g' that are not contained in x times the kernel? Well, to answer this, let's just pluck any two elements from capital G, x and y. Suppose they're not equal, but suppose that phi maps them to the same value, g'. Now let's draw some implications of this statement here. Let's draw some implications via right side multiplication of the inverse of phi x. Of course, when we do that to the right side, then that right side is E'. The left side, though, I can rewrite as phi y times phi of x inverse. I'm allowed to do that by something I proved in the previous video, and by the definition of homomorphism, I have the following. This implies that y times x inverse has to be a member of the kernel. And via a little right side multiplication here, I'm going to skip a few steps, but right side multiplication here, y is a member of the kernel times x. And now exploiting normality, y is a member of x times the kernel. So the answer to this question is no, and we are done with proving the claim. This is a hugely important claim, and we will see why on the next screen here. So here again are G and G', homomorphism phi. So we've just proven that kernel by definition goes to E'. And now, let's call those elements G'1, G'2, and G'3. We have that these further subsets, indicated by three red ovals, again, all disjoint, they can't overlap, otherwise one thing would map to two different things. Let's call that top one x1 times the kernel, the bottom one x2 times the kernel, and the rightmost one x3 times the kernel. Those are a set of all elements that map to G1', G2', and G3' respectively. Now here is the interesting question. What if the kernel is just the identity element? Well, then that leftmost oval shrinks to 1 point. That topmost oval shrinks to 1 point, namely x1. That bottommost oval also shrinks to 1 point, namely x2. And the rightmost oval shrinks to another, again, 1 point, namely x3. And what we have here is an injective homomorphism, which immediately implies that G is isomorphic to the image of phi. They have the same internal structures, the exact same internal structures, and if phi happens to be surjective as well, then phi is bijective, and we have G is isomorphic to G'. So again, big takeaway from this last slide is that if your kernel is just the identity element, you have an injection.